Hello everyone, and this is a continuation from electromagnetism lesson. For this today's session, we are going to explore how the solenoid, as shown in this diagram here, how the solenoid is able to concentrate magnetic field lines and results in a strong electromagnet. Now what I'm going to require you here is that if there's a need to, please pause the video and try to understand. I'm trying to use visualization to explain it to you, and I'm not so sure whether the diagrams may get a bit too complicated, but I'll try my best. So in order to understand it, we must first study the current flowing through the coil. And what you notice is that for the current flowing through this coil, as shown in this diagram here, over here, as I've indicated, sorry, I think I use a red marker, should be better for you. The wires at the bottom of the solenoid are actually flowing out of the plane. Okay, all these are actually flowing out of the plane. The current is flowing out, and when the current flows to the top, the one I circle at the top, the current is actually flowing into the plane. Okay, the current is actually flowing into the plane. So in order to understand how the magnetic field lines are concentrated in this coil, we will first study the magnetic field around one current first. Then we slowly put them together. So just for a quick reference, the current at the bottom is coming out of the plane, and the top is going into the plane. I'll just multiply it a few times to give you a rough idea of what it's going to be about. Now, when a current flows out of the plane, the direction of magnetic field is anti-clockwise, as shown here. The current in this magnetic field is anti-clockwise. Now, what happens when we put two of these wires together, close together? So when we have two current that's flowing out of the plane, this is what, maybe I'd like to add on first. For the purpose of helping you understand this, I'm just going to draw only one magnetic field line per current. By right, there should be many magnetic field lines, but for the purpose of explaining how magnetic field lines are concentrated, I'm just going to draw only one magnetic field line per current. Now, what I have here is a current coming out of the plane, and if I put another wire near it, so there's going to be two currents coming out of the plane. Now, when there's two currents coming out of the plane, what do you notice about this? Do you notice that in this region, there are now more magnetic field lines? One set of magnetic field lines contributed by one of the wire, and another set of magnetic field lines contributed by the other wire. So the number of magnetic field lines here is contributed by two wires. Two current. And what if I put another wire beside it? Right? So we are getting our number of magnetic field lines starts to increase. And when we put many of these wires together, alright, we are increasing the number of magnetic field lines, and hence, because of that, the magnetic strength increases. So the magnetic strength here and here increases. It's these two sections, right? Because the lines just keep adding and adding and adding, each wire contributing to the addition. So what can you see here is that when I position the the current flowing out of the plane in this way, isn't that the same as this? Right, as I indicated, when you go back to the solenoid, it's the same as this one. Right? Okay, let's park that aside first. Okay. Now what happens when the current flows into the plane? When the current flows into the plane, the direction of magnetic field is clockwise. And the same explanation goes, right? And we have, when we put two wires together, we put two current together, sorry. Okay, wires of current, they should refer to the same thing here. When we put two current flowing in the same direction together, that means they're flowing into the plane. Can you see that the magnetic field lines in this region where I circle has increased, and hence the magnetic strength in that region also increase. And so when I put some more field lines together, some more wires together, and I put some more wires together, right? Now you can see the number of magnetic field lines I circle here in these two regions have actually increased, and therefore the magnetic strength in these two regions has really increased significantly, right? Each contributed by individual wires, by the magnetic field around individual wires. And this region here, where I put in a box, isn't that the same as this region here? Right? They're the same thing. Now when we coil the wire around an iron bar, and we put it in the coil, one side must come out of the plane, the other side must go into the plane. And I'm going to bring them closer together. And can you see that? Sorry, before I bring them closer together, can you see that for the current flowing into the plane, the general direction of the magnetic field is in this direction, and for the top is the other direction. And for the current flowing out of the plane, the general direction of magnetic field line is in this direction, and the bottom is the other direction. So what happens when we put them together? So when we put them together, the number of magnetic field lines going in the same direction, the number of magnetic field lines going in the same direction has already increased by a lot. Not only contributing by individual wires, individual current, but all the current that's put together, each contributing its own magnetic field lines. And hence, the magnetic strength in between these two sets of current is very strong. If I'm able to put an iron bar here in between them, okay, it is made of iron, alright, the thing about iron is that it has the ability to concentrate magnetic field lines. And that is why usually for solenoid, we put an iron bar in the coil, and then we can make an electromagnet, which is very, very powerful. To make a strong electromagnet, right? The magnet run by current. Okay. First of all, we increase number of turns in the coil. Increase the number of turns because based on what I've shown you just now, the more turns are there, the more current, the more concentrated, the more magnetic field lines contributed by each current. Okay, and also generally when you increase current, or also you can say increase potential difference. Alright, they remain the same thing. Okay, or we also can say decrease resistance. Right, all these mean the same thing. Okay, so once there's more current flowing through the circuit, for each current there'll be more magnetic field lines, right, to make a strong electromagnet. And last of all, use an iron bar because iron is able to concentrate magnetic field lines and make very powerful electromagnets.